So some of you have heard that there's an election coming up. A few of you are familiar with that? Yeah. And so I wanted to actually start by mentioning a couple things with relation to the two prior speakers with respect to Jonathan's talk. Some of you have read an article I wrote about a year ago called Decertifying the Worst Voting Machine in America. Somebody asked me actually how I decided this was the worst voting, or who gave me the permission to say it was the worst voting machine in America. And the answer is I had written this whole blog post about it for the Princeton Freedom to Tinker blog that was started by Ed Felton. And I clicked submit and it said, you need a title. And I said, okay, decertifying the worst voting machine in America. And that's how it happened, is I just needed a title and I wanted something catchy. And the reason I called it the worst voting machine in America was I had suspected it was really bad, and when the state of Virginia actually looked at it, they discovered it was much worse than I expected. It used WEP, which is what Jonathan's talk reminded me of, but it didn't just use WEP. It used WEP with a hardwired key of A, B, C, D, E. It turned out that that wasn't the end of the problems. Once you figured out this very secret key, it had Windows File Services enabled, and the admin password was admin. And then it used, but it's okay, it encrypted the votes in a Microsoft Access database using the old version of Microsoft Access where the encryption key was actually kept in the database. And so you can download a free tool to extract it, so you could extract it and you could manipulate the votes. And there were no logs or anything like that. So the point I'm making in all this is that what we think of as secure, when that system was built in about 2000 is when it was done, we weren't carrying around with us little hacking machines in our pockets. And so the threat model was somewhat different. WEP wasn't known to be broken, although by the time they started selling the machine, it was pretty obvious. And so sometimes we need to take not just a look at, well, what's broken today, but also what's going to be broken in the future. And so I'll be covering some of that. And then with respect to Lori's talk, I wanted to, again, we have to think about the human element of it. And I love listening to Lori. Lori always has such great anecdotes, and I have one that I think almost matches some of your anecdotes. So I'm a poll worker. I've been a poll worker on and off for about 5 years. Avi Rubin from Johns Hopkins encouraged me to do that, and it's really eye-opening. We as scientists can critique stupid things that vendors do and things like this, but sometimes seeing what happens in the real polling place is a really eye-opening experience. And so in my state of Virginia, we're in the process of moving towards optical scan. I know a lot of people say, why are you going back to the future? Blah, blah, blah. That's a whole other story. But in my county, we've moved to optical scan. And so a couple years ago, I handed a voter, an elderly voter, one of these optical scan ballots. And I said, color in the circles for the candidates you want. She said, okay, and put it in a folder to protect the privacy and sent her off. And about 10 minutes later, 15 minutes later, which was a really long time for a simple ballot, she came back and put it into the scanner, and the scanner rejected it. And so I asked her permission to look at the ballot, because secret ballot, you always have to ask permission before checking the voter's ballot. And she had in fact done exactly what I told her to do. She had colored in the O's and the C's and the R's and the E's and every other letter that had a circle in the candidate's name. She had colored in all of the circles in the name for the candidates she wanted. I had given instructions that weren't exactly user-friendly. Now, to most people who have taken SATs all their lives and GREs and all the other bazillions of standardized tests that most of us grew up with, when I said color in the circle by the candidate's name, it was pretty obvious what I meant. But every year when you look at election results, and if you've ever had the opportunity to be part of a recount or an audit, it's really interesting. There's always about 1% of the voters will circle the candidate's name or cross out the name of the person they don't like or write no or yes or all sorts of other things. So we need to think about usability in the context of ballots also, and there are folks who are doing this. I don't mean to make it sound like there aren't. Whitney Quesenberry does a terrific job, and read her stuff if you're interested in that. So I just want to comment that there are, even in things like elections, which seem relatively straightforward, there's all sorts of security and privacy and usability issues that we need to think about. So what I'm going to talk about this morning, and I recognize the risk of being between you and lunch, which is better than the risk of being between you and beer, but is I want to talk about what happens after we fix all the security bugs. And yeah, it's going to take a while, but we're on the road there. So I call this, as I said, secure development after security bugs. And Gary McGraw, who many of you know, talks about security bugs and flaws. And by bugs, he means many of the things that cause buffer overruns and stuff like that. And by flaws, a lot of times what he means is things like what Jonathan talked about, where people just misunderstand how to build systems securely. And so I'm going to be talking more about things in that latter class, but even beyond crypto. So oh, I forgot. I'm not used to having one of these things down here that I can look at, so I don't have to keep looking over my shoulder. So what this is about is more than just avoiding buffer overruns, SQL injections, all the things that we're used to, but looking at new classes of vulnerabilities. Largely, we build software today the same way as we did 20 years ago, but we need to look further. And so what I'll be talking mostly about is what are called side channels and algorithmic exploits. And many of you will be familiar with these, but I want to talk about how we find them in the DARPA, through the program at DARPA called STAC. And I guess this is the point I wish to mention, the same sort of disclosure that Lori did, which is these are my opinions only, blah, blah, blah. Okay, so on the left side here we have a nice graphic of the prevalence of various kind of vulnerabilities. Many of you have seen things similar to this. This one is from Microsoft, showing that over time, the use of technologies like address space layout randomization and data execution prevention have significantly reduced the number of, or the percentage, excuse me, of vulnerabilities that are exploitable in Microsoft code. Not to say they've gone away entirely. We still see these periodically. And in a lot of other products, like some IoT products, these things still crop up on a regular basis. The total number is still going up, I believe, but as a percentage, it's getting better. But what I'm interested in here is the gray part of this left-hand scale, which is the stuff that we don't have tools to fix today. Algorithmic complexity attacks and side channel attacks. And these are happening. They're not nearly as common, and they're a lot harder to fix, but I'm going to give you a couple examples and then walk through them, and then I'll talk about some lessons learned. So this first example is one that I love because I learned about it when I was an undergraduate, and from my gray hair or lack of hair, you can know that that was a long time ago. This particular vulnerability was discovered in the early 1970s in the 10x operating system. How many in here have ever heard of 10x? More than I would have guessed. 10x was a fairly popular operating system. A version of it called TOPS 20 was sold by Digital Equipment, which was just down the road here. And 10x, I believe, was developed right here in Cambridge. I don't remember who, but it was developed somewhere here. So the vulnerability was a simple one. Let's imagine that we have passwords were stored in clear text. And I'm trying to guess Rob's password. And for the sake of argument, Rob's password is secret. And I told you not to tell. I'll try to remember next time. So the way this vulnerability worked is the attacker would guess A, XXXXX, and then B, XXXXX. And let's assume for the sake of argument in fact, what did happen is it would check one character at a time and would return as soon as it got an error, a mismatch. And so by looking at how long it took to get the error back that you got it wrong, I could tell, did I have the right first letter? Because if I said AXXX, it would take 1 second to respond. BXXX, it would take 1 second. CXXX, 1 second. SXXX, it would take 2 seconds. So now I know the S is correct, and I have to guess the next character. So now I can clearly guess the password in time proportional to n times m, where n is the number of characters in the password, and m is the number of different values for each character, instead of n to the m, which we all know is a good thing. Now, this doesn't contradict anything that Lori was saying about choosing passwords and changing them and everything. This is about storing, how passwords were stored and checked. So the idea here is that we would like to be able to find vulnerabilities in software that do the character by character check, as opposed to the proper way, which is, of course, using Jonathan's crypto stuff. We should be storing a one-way hash and storing it salted and all those things that a lot of programmers don't do correctly. But if they were done correctly, they would prevent these sorts of attacks because it wouldn't be possible to check one character at a time. So a bit of trivia about why this was exploitable, which will come into play on the next slide, is even in a modern system, even if someone checked it one character at a time, it wouldn't be that big a deal because you'd be checking, you wouldn't be able to measure the time difference unless you were extremely close. And by extremely close, I mean you're running on the same computer and you have a very precise timer. Well, it turned out that the way that this one was exploitable took advantage of another aspect of the system, which is what you would do is you would put the password, so the first character of the password was in the last byte of a page of memory, and the rest of the password was on another page of the memory. And then you would force the second page to be swapped out to disk, and there was a way to do it, just trust me on that. And then by checking whether you got a response effectively instantly relative to the cycle time of the machine, which was about 1 megahertz, or whether it took a long time relative to the 30 milliseconds that it would take to read a page from the disk and get it back into memory. The difference between 1 millisecond response and a 30 millisecond response in round numbers was enough that you could very, very clearly tell whether you had hit the memory, whether the character was right or the character was wrong. So today, it would be, and then what you would do is once you got the first character, then you would shift everything over by 1 byte. So now you have 2 bytes on the page that's in memory and the rest of the bytes that are on the page that are on disk. Again, you go through the same thing. Today, this would be a lot harder to do. Does it mean the problem doesn't exist anymore? Let's assume that you implemented it. No, the problem still exists. The vulnerability still exists. The question is whether someone could effectively take advantage of it. So this study, excuse me, and this was done by Apogee Research, and I appreciate their help, is they fuzzed the data and they assumed that each character was, that the delay per character was 100 microseconds, and that there was a standard deviation, as you can see in the upper right, of 14.4 microseconds, excuse me. And they did these they did 10,000 samples. And you can see, if it's a 1 character password in the upper left, you can see a very clear distinction between yes and no. So you could clearly tell a 1 character password whether you got it right or not. With 16 character password, because you had to do the same exercise 16 times to find each character, it becomes a little harder to tell whether you got it right or not. By the time you get to 64 characters, it's really hard to tell whether you've got the password right or not, because there's so much overlap between the right answers and the wrong answers. So what's the message from this is the same vulnerability might or might not be exploitable. We have to say, when we talk about a vulnerability, we have to talk about, could someone do enough tries, because to do enough tries with a 64 character password, they would be pounding the system with password check requests, and it would sure look pretty funny in an intrusion detection log, for example. But if they can do it quickly or with fewer tests, then it wouldn't be so obvious. So the point here is that you need to think about not only is it vulnerable, but how vulnerable is it, and can you quantify that? So let me give you an example from the STAC program. The STAC program, and I never remember what the acronym stands for, but it's looking at side channels and algorithmic complexity attacks. So this sample program in the upper left, obviously a pseudocode, has two nested loops, and there's the question that we're asking the developers is there a vulnerability in this program such that given an input n, which is less than or equal to 99, is there a vulnerability in this code for which they only have the Java bytecode, they don't have the source code? Is there a vulnerability such that you can make this program run for more than 60 seconds? And the natural tendency is to look at the innermost loop, because that's what we as computer scientists do to figure out algorithmic complexity. And in the innermost loop, you'll never run more than 1 millisecond. And so even if we run it 99 times, and even if we run the outer loop 99 times, then 99 times 99 is not going to be a problem. But we actually need to also look at the time spent in the in the outer loop, and that's a tendency that we as programmers tend to ignore because we assume the complexity is in the inner loop, not in the outer loop. And so this is the sort of scenario that might happen if you're looking at code that is receiving requests over a socket or something like that, and then processing them. We might look at how much time does it take to process each element in that request, and not look at how long is the basic overhead of processing one request altogether. So in this case, there is a vulnerability because the outer loop takes a long time to run. So there's a second question that I asked, and this one is a trick question, which is, is there another input, n, such that the value of n could be leaked as a side channel? And I haven't provided enough information here in this pseudocode, but in fact, I'm going to just say for the sake of argument that the answer is no, because there's nothing showing space usage. And the reason I'm showing this is that in a moment I'll show you we have programs and questions. So let me show you one more example, which is this code, which can anybody see what the space and time complexity difference is on this? Anyone? There's a hint in there, but I'm not sure if anyone can see it. Well, the answer, and I don't have a pointer here, but if t is equal to 2, then if t is equal to 2 and guess is less than or equal to secret, then you get code that is proportional, the running time is n squared, and if t is equal to 2 and guess is less than secret, then you get time proportional to n. This isn't an algorithmic complexity attack, this is actually a side channel attack, because in both cases, the worst case time is proportional to n squared, but you have one case where you can get you get one case where it's different. So the point is you have to look at the whole program, and it's a little trickier to look at the whole program than just looking at lines of code in isolation. So how do we run this program? So we have two red teams that create vulnerable programs. They're dummy programs. They're based in most cases on open source software, and they've got vulnerabilities added. And the idea is that we ask a set of questions, and I showed you a couple of samples of the questions we asked. And in our first couple exercises, we had 19 vulnerable programs, and we had 42 questions. And the correct answers to some of those 42 questions was yes, and the others, it's no. So we have 8 research teams, and there are several people in the room who are parts of some of those research teams. If they want to identify themselves later, they can, but I'm not going to out them. We have 8 research teams, and we have 1 control team. The control team uses existing commercial and open source tools to try to find the vulnerabilities in the code. Again, this is Java bytecode that they're looking at. And they spend a certain amount of time that I'll go into in a moment, and they look through those programs, try to answer as many of the 42 questions as they can, and they don't just answer yes or no, they answer yes, and here's how we found a vulnerability and why we found a vulnerability, or no, this is why we don't think there's a vulnerability. The results of this are scored by an engagement lead team that gives ratings, and you can see some actual numbers from one of our engagements there, but I'm not going to tell you whose numbers are who. So what I gave you before were some sort of dummy, simplified examples. I'm going to give you one real example. This is the Gab feed program from the STAC program, and this one was developed by Cyberpoint, and I appreciate their help as well. So Gab feed is a program that just looks like a web forum that you can write postings to it. People can make comments on the postings, things like that. It's sort of a pretty simple website where people can post things. And the questions, so the developers of the vulnerable program created specific vulnerabilities. And in this particular program, there's going to be 2 actual vulnerabilities and 1 thing that looks like a vulnerability but isn't. So I'm not expecting you to read this, but if you're familiar, this is a Sidechannel that allows you to determine the RSA key from a website with particular manipulation of the parameters in negotiating the keys. And this was, Tim, do you remember which conference this was published at? No? Okay. Okay. So the question that gets asked to the research teams is there a side channel in time in the challenge program from which a third party can discover the server's private key used in the server authentication? They're allowed to do passive operations, which are monitoring the network and seeing seeing the packets, and each time they capture a packet, that costs them 1 point. They can also do active operations. They can issue an HTTP request and receive a response. Each of those costs 1 point, and they're allowed a maximum of 60,000 points, and they have to capture the password within with a probability of 95%. And so this would be a sample question that we might ask a research team. Second question would be a time complexity vulnerability, and we're asking, is there an algorithmic complexity vulnerability in time that would cause the challenge program's real runtime to exceed the resource usage limit in the input budget? In this case, they get to examine 400,000 packets or 400,000 transactions, and they're looking for this vulnerability, which is a JavaScript, a vulnerability in the implementation of pixel width comparison calculations in JavaScript. And they get up to 300 seconds to do this. The details of what this particular vulnerability are not particularly important. I just want to demonstrate the sort of questions that we ask them. And then a false vulnerability, again, these are all vulnerabilities about this same program, Gab feed, asking whether you can send input to the program to cause it to chew up all its memory. You're allowed to send up to 400,000 bytes of data, or maybe that's 4 million, I can't read. And can you chew up 512 megabytes of memory? Again, so the details don't really matter. The point is that we're asking them questions and asking them to analyze the programs and figure out the answers. There's a number of different factors that the research teams are trying to figure out and to determine whether these programs are vulnerable. is there a data guard? For example, there might be a limit in the code that prevents you from sending too much data or too large a number or whatever, and that might provide a protection. There might be coefficients in the algorithms that prevent the usage from growing too fast. And then there's the complexity of the algorithm itself, which drives the memory usage, the CPU usage, et cetera. And so the idea of the defense teams is to try to figure out, for a given program, given a particular set of inputs, is the performance going to be above or below the red line, the horizontal red line that is the vulnerable performance, and assuming that you have the input to the left of the red line that's labeled input budget. So we've done a couple of these exercises. As I said, the first 2 exercises we did, we had 19 of these vulnerable programs. We asked 42 questions about them. Not everybody answered all of the questions. You can see off on the far right, the red dot and the purple square. Those 2 teams answered all 42 questions. On the far left, one of the teams, the purple diamond, answered 4 questions. So there's a pretty wide range. In large part, this is because the teams are learning to operate in the exercises, and they're learning to make their tools work effectively. So there's a pretty wide range at this stage of the game. We're doing a 3rd exercise in January, and hopefully from that exercise we'll have a better idea of what works and what doesn't. Turns out there's a number of challenges in doing this. Well, one of the challenges is that some of the test programs actually have vulnerabilities that we didn't intend to have. And that makes it a little harder to do scoring because if somebody finds a vulnerability, then if they answer yes, that it is vulnerable, we have to say, oh, wait a second, we didn't think it was vulnerable, or we thought it was vulnerable in a different way. We have to go back and figure it out. And in some of the cases, in fact, the research teams have found vulnerabilities we didn't know existed. And so we've changed ex post facto, we've actually changed the scoring to give credit to people who found vulnerabilities that we weren't expecting. The different teams are using a wide variety of different techniques. Everyone's using some form of static and dynamic analysis, and pretty much everyone's doing information flow analysis and taint analysis. They're also using a bunch of other different techniques. Again, I'm not going to go into these. I just want to tell you that there's a lot of different ways to skin the cat. And there's not, at this point, a clear answer which is the best way to do it. We've run into some challenges. Getting research teams to answer that programs are not vulnerable is a lot harder than it seemed because it's much harder to answer no than it is to answer yes, and this has a really bad side effect because what we really want to know is which programs are safe to use, not which ones are dangerous to use. But if you don't have a sound solution, you will never be able to answer no. We're having some more programmatic challenges, like how do you balance the effort doing research versus the effort doing the experiments? How do we deal with the changes in technology evolution, and so on? So we are still, this is not a perfect system where we know all the answers. We're still evolving. Now that I've sort of told you about what we're doing in the STAC program, I want to step back and think about, so why should we care about this? Are side channels important? And I think Jonathan made the excellent point that there are times where we go looking for vulnerabilities and we find vulnerabilities that are there in principle, but in fact they're not exploitable, they're not usable. So I want to give you a couple of examples of things where the same piece of software might in fact be vulnerable in one case, or might always be vulnerable, but we care about it sometimes and we don't care about other times. So let's imagine that I've built a website, an e-commerce website, and I'm selling the software commercially. And there's something really screwy about the way I implemented it, and I don't, it doesn't really matter why it happened, but there's only 3 things that we're selling in this e-commerce store. We're selling cell phones, refrigerators, and breakfast cereal. And I can tell which one of the 3 things you ordered by how many bytes the response is or how many microseconds it takes to get a response. It doesn't matter. But I can clearly establish, even though everything is encrypted, by either looking at timing or space, the number of bytes, I can tell what you ordered. So I might want to use that if you're ordering a cell phone. That might be interesting because I can steal the cell phone out of your mailbox when it arrives. Kind of hard to get a refrigerator into a mailbox, so that one may not be exactly the same threat model, but I'm going to steal Rob's brand new cell phone because I see that I'm sitting in the same. You got one? Is it one of Lori's iPhones that? No. You like Lori, good. But if I'm sitting in the same coffee shop, I can observe this sort of stuff, and now I know whose mailbox I want to be looking through. So this is, kind of a small threat. Is anyone really going to care about this? Probably not. But now I'm using that same software, and I'm going to use it for ordering over-the-counter pharmacy products. Now I'm a little more interested in the privacy issues of knowing what Rob ordered, whether he ordered antacids, a paternity test, or anything. No, I shouldn't pick on Rob. I'm sorry. So the same software, nothing about the software has changed except where we're using it. And yet the threat model has changed completely. So do I advise a programmer who is writing software that's going to be used for an e-commerce site, hey, you better be really worried about side channels for space and time because someone might be able to figure out what products are being ordered. I mean, that's kind of ridiculous at one level. Who cares? But especially if I take that same software, now I'm using it for ordering prescription medications, and now it becomes really sensitive if I can detect this. So exactly the same software, but now being used for a different purpose. And I think this is something that we don't think about enough, is we think about just the software in isolation, and we don't think about more broadly how we use it. So what do? I don't have the answer. If I make everything a constant time, constant space operation, which would be the way I would solve the problem that I pointed out on the previous slide, well, we as programmers are taught to make things run fast. Who's going to go to their boss and say, I've got a great improvement in our e-commerce software. I'm going to make it run slower for everybody. Is that a sales technique that's going to work? No. Everyone wants to make everything run fast. And so to make everything constant time or constant space isn't a solution. But on the other hand, there are times when it has to be. For, say, where we're using encryption keys, or where we're sharing encryption keys so that we don't get into the side channels that allow leaking RSA keys. Do we introduce more noise to make it harder for the attacker to figure it out? I don't have an answer, but my purpose in raising this is as we think about developing software and methods we use for increasing the security of software, we need to think about not only the security of the software in isolation, but the security of the software in the context of how it's going to actually be used. So can we can we train developers and analysts? Yeah, but who, thinking to the e-commerce example, who's going to provide the guidance to programmers and designers that this is a case where you need to worry about side channels, and this other one over here, oh, that doesn't matter. It has to be part of the design process. It's not something we can add in after the fact. Also, a lot of the problems we see in side channels come not from the code, the custom code that's being written, but from the third-party libraries. If I let's say I get a new version of the JVM, and the new version of the JVM uses a different sorting algorithm than we had in the previous version. The performance may change, even though the application itself didn't change. So many years ago, I was working as a database consultant, and the database vendor, the DBMS vendor, did an update from version 3 of their software to version 4 of their software, and in doing this, they changed one of the critical algorithms from being an order n log n algorithm to an order n squared algorithm. And you sort of scratch your head and say, don't you mean the other way around? And I said, no, I don't. They really changed from an n log n algorithm to an n squared algorithm because all of their test cases had small n's, and so and the coefficients were such that all of their test cases, an n log n algorithm was worse than an n squared algorithm, which all of us in this room hopefully know why that's a bad thing. But in that case, an application, although side channels weren't the concern, an application that was built on top of that database system without any change to the application itself might have gone from being safe to being vulnerable because the difference in the n squared algorithm was so bad that something that previously wasn't measurable now became measurable. Although that may not happen routinely in our libraries, we have to recognize that as libraries get updated, the things that we're relying on change, the algorithmic complexity may change, and the result of it may be that programs become vulnerable even if they weren't. So we can't just say, oh, this is safe, we're safe for all times. So I think my message to you is that when we think about secure development, we need to think beyond just, is this particular code vulnerable to a buffer overrun attack? Does it have a crypto algorithm implementation flaw? But what's the next generation of vulnerabilities we're going to run into? Maybe it's things like side channels and algorithmic complexity, which are sort of emergent properties of software and not directly things that we can see by reading the code. And I think that's it. Thank you. And there's a few minutes if anyone has questions, or lunch is probably waiting for us. Or beer.
We're not going to let you go that easily. So as before, if you have a question, please come up here. If it's okay with you, I'd like to ask the first one. You picked on timing attacks and space attacks, but you didn't say anything about power attacks. And in a world where we have to always recharge our batteries, side channels related to how much power is being used by a particular algorithm is also one of those things.
Sure.
Is DARPA working on that? How do you see that in the scheme of these things? Do they relate, or is there something unique perhaps about those?
That's a good question. This particular program is only looking at time and space attacks through side channels and algorithmic complexity, but there's another program being run by Angelos Karamitis that is looking at some power usage attacks. Do you remember the name of it, Tim? Yeah, LADS. I believe that's the LADS program. And looking at analog as well as digital aspects of, can you measure the analog emanations from a chip and get side channels through that. There's been a number of interesting papers also not relating to DARPA, people using the accelerometers on phones to measure disk movement. If you can put your phone on top of a server and you can measure the movement of the arms in a hard drive, and you can actually determine what operating system is being run. I mean, there's a lot of caveats on this, but there were some interesting papers a few years ago. So there's a lot of different side channels, and negating those sorts of side channels makes negating software-based side channels look like child's play.
Okay, next question.
So with any of the timing,
You want to tip it up to the microphone?
with any of the timing channel attacks, are any of them based on, is the Java as a garbage collected language using the garbage collector in this work?
So that's an interesting question. When the program started, the intention was to include garbage collection as one of the aspects to be measured. So far, we haven't put a focus on that, but I'm expecting we will further on. It's a little bit tricky to decide how much to put on there because it's something that there's very little control over. It's just like I was giving as the example, the database algorithms. If there's a change to the garbage collection algorithms, then the vulnerability of applications will change. One thing we do to limit or to make it even feasible is we have a defined version of the JVM. We have defined hardware, et cetera, because if we didn't have that, then what you tested and what she tested would be completely different, and you wouldn't be able to answer the questions at all. You have to have a controlled environment. But it is a difficult question whether to include garbage collection. Yeah.
Daniel Bilar from Visa. I have two questions. The first one relating to the algorithmic complexity question. As I understand it, Peter Slatko, Mudge, unveiled in Black Hat together with his wife, CyberWell, software scoring system. One aspect of that was indeed scoring software according to algorithmic complexity attacks, which is an extremely hard problem for imperative languages, even very hard for functional languages. Do you have any interaction with the CyberWell, and is there any cross-pollination?
I have not talked to them, although as it happens, my office used to be Mudge's office, but unfortunately the wisdom didn't seep into me with the furniture. I think that's an interesting question, but I haven't done anything in that space yet.
Yeah. The second question relates to the timing channels. So I think your donation chair, Jason Syverson from Siege, pointed me to a paper a long time ago that actually proved that you can never undermine these side channels. You can limit the bandwidth and the rate. So I think it's a little bit of a lost cause trying to keep them down, trying to eliminate them, but it's not a lost cause limiting the useful bandwidth. So, but it's too much to ask of developers to be able to go through this. Right. As I'm wondering, have you ever seen tools that you could put into a continuous integration pipeline, a Jenkins plugin, anything like that, that would help even just pinpoint that there may be timing side channels, because that would be actually of practical value. Right. I cannot tell the developers to write this correctly because they have to have deliverables. But if I can automate it, then I can. Have you seen something like that?
Yeah. So this program was invented by Tim Frazier, and when he asked me to take it over, the first thing I thought is back to my early days in the security field, where we talked a lot about covert channels, and there were a lot of proofs. If you go back to the 80s, a lot of people proving that covert timing channels and covert storage channels really were the same thing. You could convert one to the other, and I think your point is a correct one, that you can never totally eliminate these, especially the timing channels. The best you can do is reduce them and measure them. So I don't have any hope of completely eliminating them, but I do have a hope of making them better. With respect to the second part of your question about tools that could help someone identify the problems, in fact, that's my hope, is that the outcome of this program will be tools that will someday get incorporated into Eclipse or whatever else that will help people identify the potential vulnerabilities. You'll still have to have tuning knobs, because this isn't a binary question. It's not like there either is a buffer overflow attack or there's not a buffer overflow attack. In this case, it's there is a timing side channel or there is a storage side channel, but is it bad enough that you need to worry about? That's a separate question. And so hopefully we'll have these tools with some appropriate knobs that people will be able to try those questions. I don't think we're anywhere close to that today, but that's the goal.
Thank you.
Okay, so in some sense, this has been a very depressing talk, basically.
When have you ever heard a security talk that isn't depressing?
There are some. So, I mean, back in the old days, to be a good programmer, you had to know sort of maybe that much about secure coding, and now you read 2 yards full of books on secure programming and have to try to know all of this. And you seem to be adding yet more details in this things, and even tools. There's only a limited number of tools that programmers, can run or even understand what the output means. Is there any hope that you can see of which you can reduce the amount of superhuman abilities that programmers have to have?
I think the important thing is to start by recognizing that the class of vulnerability exists and that we have to think about what cases we care and what cases we don't care. So to go back to the example I gave, if the vulnerability allows me to differentiate between Rob ordering a refrigerator and a cell phone, it's really not that important. Well, it might be to Rob, but it's not nearly as important as the pharmaceuticals case where we really have to pay attention. So getting designers to start by thinking, gee, how sensitive is this information that the side channels might matter? I would bet that, just to pick on e-commerce sites, I bet that there's nobody in the e-commerce world who is thinking about these sorts of things. And until they think about it, until they recognize that a problem exists, there's no chance that they'll come up with solutions. So I'm hoping that I'll be able to get people, perhaps from the banking industry, they tend to be a little bit more bleeding edge because money, that they may show some interest, and that may be an early test case for can we simplify these things both in the prioritization phase and then in the actual engineering phase that we can use these appropriately.
So I want to weigh in on this just a second myself. I don't think this is at all a depressing talk. We put together this conference, and I guess it's possible that we thought that we would do this once and we'd then have educated everyone and it would be done and we wouldn't have to come back ever. But Jeremy has made it very clear that it's not going to be simple. We will not solve everything today or tomorrow. And we're going to need to do this a couple more years before we have everything solved. So in that sense, it's extremely positive. So let me finish by thanking very much Jeremy for coming and giving us a talk, giving us hope for future conferences. Thank you very much, and please thank our speaker one last time.